Okay, so first we're just going to recap a little bit. So I have a few statements here for you. You want to decide if the description is a vector or a scalar. Remember, a scalar is just a number. So the first one is the car is traveling at 50 miles per hour, and 50 miles per hour is just a speed. Let me get a highlighter here. So if you look over on this little list I put over here, speed is a scalar. So 50 miles per hour is scalar only. I shouldn't have said no, I should have said scalar. So this is a scalar because this is just speed, it has no direction. All right, and then if the car is traveling 50 miles per hour due north, so then that would be velocity. So that one would be not yes, that one is a vector as it has magnitude and it has direction. All right, a football player is running 5 miles per hour towards the end zone. It's a little bit harder to figure out, but this one is a vector because it does have that speed of 5 miles per hour, and it is telling you the direction it's going in. It is saying it's going towards the end zone. And then finally, the volume of a box at the west side of the building is 14 cubic feet. So when you look over here, mass, you could kind of consider this mass, okay? Kinda. The west side of the building, I think sometimes makes it feel like it's supposed to be a vector because it feels like it has direction, but it really doesn't. That's just a location. Okay, now we're going to do another little bit of practice here. So we're going to add these vectors together. It is always very tempting for students to just take and add the two endpoints of the vectors together, but that is not how we add vectors. We add them by combining or taking like a tip to tail, so combining the x's and combining the y's. So something that you can do if you prefer is to take this vector, the 1, 2 vector here. I copied it and I'm going to attach it right on to this 3, 3 vector. So that means the actual result vector would go from the origin to that point right there. So that's what it would look like. And when I add them together, I've got this pre-typed down here for you. I'm adding the vector 1, 2 with the vector 3, 3, and we're just adding together the I components and the j components, and that would be 4 comma 5, which when you look at my graph, that is 4 comma 5 as well. So I'm going to do the same thing over here. I'm going to go ahead and make a copy of this vector. Now remember, since both of them, excuse me, are starting at the origin, the vector, like the initial point is at the origin, and then the terminal point is at this point here. So this point actually is the vector. All right, so here is the copy, which means my resultant vector is this one right here. And when I add the two of them together, I get -1 plus 4 is 3, -2 plus 1 is -1. And you can see that the result is over 3 down -1. Okay, that was a quick recap just to make sure you were getting it. Hopefully that makes sense. Now we're going to do a couple more things added on to that idea. Having a unit vector is really important in vectors in general, especially in physics, when you go on knowing the vector in a shortened version. So what I did here is I kind of did the next step for you here. Or did the final step or part of it. So here are the steps that you're going to do. So the first thing you're going to do is you're going to find the vector P1, P2. So P1 is 2 comma 6, which is what was supposed to be graphed here until I actually accidentally moved it. And then the terminal point is at -4, 9. So that's this point over here. So this is the vector floating kind of in space. But you remember, vectors really get shifted down to the origin. So when I find the P1, P2 vector, I am just going to subtract the terminal from the initial. So, or sorry, the initial from the terminal. So -4 minus 2 is -6. and 9 minus 6 is 3. And you again can see that with the graph I created. So this is the P1, P2 vector. Then I want to find the length of that vector, and that is just Pythagorean theorem. So I'm going to do 6 squared plus 3 squared, which is 36 plus 9, and then the square root of that. So 36 plus, oops, 36 plus 9. I don't know why I typed it up there, is equal to 45. I want the square root of that, so I think I'm going to draw the square root in by hand here. Okay, so that's the length or the magnitude of the the vector. Then to find the unit vector, you take the original one and divide by the magnitude. Notice I didn't even bother to simplify. It doesn't matter. If you would prefer to have that root 45 simplified, go for it, but it is not necessary. And I wrote it in what's called component form, but we also could have done it as negative 6 over root 45I plus 3 over root 45J. That's the other way of writing this. Okay, so now number 4 says, write a vector an AI plus BJ form given its magnitude of 6 and it makes a 60-degree angle with the positive x-axis. So again, I typed up everything first so that you'd be able to read it as opposed to this awful handwriting with the mouse. So you're going to start by knowing that the magnitude is 6. So that's going to go out front of the vector. So 6. And then we're going to write it with the cosine and sine in there first. So 60 degrees goes in for cosine and sine, and then you're just distributing the 6 inside and simplifying the cosine and the sine. So one thing you could do is think of exactly where that's at. It's kind of like a polar problem almost, where you've got, let's change the color here, this vector at the 60-degree angle, so it's there. Okay. And its length is 6, so it's kind of like it's on like the 6th circle, if you want to think of it like that. So you're really taking the unit circle value and multiplying by 6 and then writing it with i's and j's. So it's really not changing too much from what we did last chapter or last unit. All right, this is one of the harder ones we do. The students tend to struggle with this, and there is one like this on the test and maybe even on the final if I'm remembering correctly. So make sure you're writing this down well. So you've been given this magnitude of 20. So you've been given the length and you've been told a little bit about the components, but not their values. You've just been told that the component in the negative I direction is 4 times that of the component in the positive J direction. So we're going to end up setting up um, an equation that we're going to solve. Okay, so let me start by writing this out a little bit. So I started by calling my vector negative 4a comma a. Okay, so it's it's 4 times the component in the I direction is 4 times that in the J direction. Okay, so this is kind of how I'm writing this out. I'm calling this A. And then I'm going to use Pythagorean theorem and go away, there we go, and use the answer or the magnitude that was given to you in the problem and set up an equation. So the magnitude of this vector is a squared plus 16a squared. So remember to square the negative 4 as well. So this is the magnitude of the vector I set up, but this was the magnitude that was given. So now I'm going to use that information to solve this equation. So I have the square root of 17a squared equals the square root of 20. Okay. Set this up however you want, in however many steps you need, I should say. So I squared both sides. And then I'm going to divide by 17 and take the square root of that. And then you just want to think about, well, where is this supposed to be, like when the original information was given? So technically it could be positive or negative, right? So it said that get this, make a little sense. You're going in the negative I direction and the positive J direction. So that means if this is my vector here, let me actually rewrite it out. Oh, I did. There we go. I used decimals for you. So I put this square root of 20 over 17 in for A. So that means I'm going to the left. Oops. We'll change to pen. Come on. There we go. So I'm going to the left, negative 4.399 and up 1.085. So my vector would be here. Make sense? Okay, again, remember you can always pause or go back and watch it again if you get confused, or send us an email if you're stuck. Okay, so now we're going to start talking about things a little more physics-like. So if you've taken physics or in physics, this might look kind of familiar. We do things a little bit different in math, so keep that in mind. Okay, so hopefully you remember that a force vector is written in this form. It really looks exactly the same as a velocity vector, just changing the v to an f. Okay, so a force of, this is 40 newtons, just a measurement of force in physics. Okay, so a force of 40 newtons acts on an object at an angle of 45 degrees with the positive x-axis. A second force of 40 newtons also acts on the same object at an angle of negative 60 degrees with the positive x-axis. Find both the direction, so that's the angle, and the magnitude of the resultant force. Okay, sometimes it doesn't even mean angle. Sometimes it just means give the x and y direction that you're going, depends on the problem. Okay, here we go. So I drew up a diagram. So I'm drawing a diagram in this manner. I'm going to label each of my vectors here. So the first one is this black angle or this black vector here. So I'm going to call it F1. And it's a 45-degree angle off the positive x-axis. So that's F1. And then F2 is this one that's, nope, sorry, over here. So I attached it. So I did what's called the tip to tail method. So I attached force 2 to the end of force 1. I could have put it over here, but then I would have had to just move it to attach it anyways. So I attached it at the end of force 1. And then this one here, this is what we call the resultant force. So this will be FR. Okay, and when we do these problems, oops, I don't want to show you that yet. You want to remember that when you add two forces together, you get the resultant force. Okay. All right, here we go. So the first thing you're going to do is you're going to write out each of the force vectors. So that's what I started with. So the first one had a magnitude of 30 and an angle of 45. I'm using I and J's in this problem, and I think I'll use component in the other one just so you can see both. It does not matter. And then I'm going to write out the second one using negative 60. You could also use 300 if you prefer. It's the same angle. Okay, and then I went ahead and simplified each of them using the fact that these were unit circle angles. If they were not unit circle angles, I don't know if I would have bothered. I would have probably just typed it all into my calculator, which all of these problems are going to be calculator problems. Okay, so there's force 2's vector. Okay, and I always like to kind of look and see, does that make sense off of my graph? So the first one is going into the first quadrant, and then the second one is down into the fourth. So positive, positive is first quadrant. Positive, negative is the second, or is the fourth quadrant. Okay. All right. Again, adding the two together will give you the result. So you have to add the I components together and add the J components together. So this would be the result vector. It's fine. It's not very friendly. It doesn't really give a good description of my location, but it is technically correct. So I went ahead, though, and changed it into decimals just because it's easier to get a good grasp of what's going on. So the result went quite a ways to the right and not nearly as far down. So when I look at my graph here, I went quite a ways to the right and not nearly as far down. Long x value, short y value. Okay, so that's the result vector. So that is the answer to the direction part. And then I have to find sorry, it's not the complete answer, but it's part of the answer to the direction. Um, to find the magnitude, so I'm going to take my decimals, but remember to use the rounded version, and use your Pythagorean theorem with these two unrounded numbers in your calculator. So 41.213 squared plus 13.428 squared, square root of that should give you this number. And then I do want to talk about this to make sure you're remembering what type of answer you should get here. So to find the angle that we are going, you're going to do inverse tangent of y over x. So here's my inverse tangent, and I'm getting negative 0.315 radians. It's totally fine to leave it like that, but remember that inverse tangent only gives you angles in quadrant 1 or quadrant 1 or quadrant 4. So if this location hadn't been in quadrant 4, you would have had to figure out how to move it by adding or subtracting pi. But you can tell that it's in quadrant 4 because you went to the right for the x's and down for the y's, which is quadrant 4. Okay? All right. So now comes the next piece of the puzzle here. So we're going to talk about what's called static equilibrium. Static equilibrium has two big pieces of information that you need to know about it. An object is in static equilibrium if the object is at rest, so not moving, and all of the forces that are acting upon it are zero. I tend to think of this as something like hanging from the ceiling, or um, something being pushed on from two different directions or three different directions even that isn't moving. It's like if you and two of your friends got together and tried to push a big heavy object, and you all pushed from different directions and it didn't move, then this thing would be in static equilibrium. Or if you were pulling on an object in three different directions and it didn't move, it would be in static equilibrium. And I say three, but it can be as many people pulling or pushing as you'd like. Okay, so here's our first example. It's going to take a while to get through, so I'm hoping that you can bear with me as we go through it. And I'm also going to show you how to do something on the calculator at the same time. So a weight of 500 pounds is suspended as shown. So we've got this 500-pound object, and it has these two cables that are holding it to the ceiling. And the cables are making these angles with the ceiling. And they must have a good, decent amount of tension in them to keep this 500-pound weight from moving. Okay, so I went ahead and drew this little diagram over here so that I have three different things that are representing the forces. So I have the force pulling the vector, sorry, the force vector pulling off to the right, the vector pulling off to the left, and then the weight itself has its own vector. So we have to set up each of these vectors. But one thing I want to point out is that they all have the same origin right here. So this angle for the first vector is 45 degrees off the positive x-axis. This angle, though, is different than what is listed in the picture for force 2. So force two's angle is actually this one going all the way to here, which is going to be 180 minus 30, which happens to be 150. And then the force 3 vector all the way off of the positive x-axis, well, that's actually 270 degrees. Okay. All right, so I have already written out each of the vectors for you, but we'll talk through it here. So force 1, I know the angle is 45 degrees, but I don't know the magnitude. So I went ahead and called that magnitude x. Sometimes you'll see like books will write it as the little, double line magnet standing for magnitude like this. And even with good handwriting, this is kind of confusing to me because I feel like it's hard to tell. You've got like all these lines going on, and you got the F here and the F here, and I think it gets a little confusing. So I tend to rename the magnitude as an actual, that's supposed to be an arrow, as an actual X or Y um, variable, which is what you're going to see in the second force. So the second force has an angle of 150, and then I'm calling its magnitude y. Again, if you prefer to call it with the double lines like this in an F2, you can. And then F3, we were actually given that the magnitude was 500 pounds, and the angle is 270 here. So we've got these three forces. I'm going to go ahead and write them out so we have them with their unit circle values. But if they were decimals, or like if this angle was like 20 or 35 or something, you would just type it right into the calculator with the angle that's there. I just want to write it out with the numbers. It'll be easier for us to look at. So here is my new force 1. I am writing it in component form again. So distribute the x, root 2 over 2x, root 2 over 2x. It's the same thing twice. And then my second force, cosine of 150, is negative root 3 over 2 times y. Sine of 150 is a half times y. And then the third force, cosine of 270, is 0. Sine of 270 is negative 1. So 500 times negative 1 goes here. So I have these three vectors. Well, what in the world do we do with this? Okay, so what we do with this, oops, I don't want you to see that yet, is we need to understand that these three vectors that we're talking about all add up to 0. And the reason they all add up to 0 is because the object is in static equilibrium. And if the object is in static equilibrium, then the sum of all its forces is 0. Okay, so that means that F1 plus F2 plus F3 equals 0. But we don't just add the whole entire, all of it together. We add together or combine the I components and J components separately. So we're actually going to create a system of equations that we are going to use the calculator to solve. Okay, so here's the first one. So the I component of the first vector was root 2 over 2x, and the I component of the second vector was negative root 3 over 2y, and the I component of the third vector was 0. Oops. And then the J component, oops here, the J component of the first vector was root 2 over 2x, and the J component of the second vector was a half y, and the J component of the third vector was negative 500, and all three of those together equals 0. So now I'm going to go ahead, I'm going to move that 500 in the second equation to the right-hand side, and we have a good old system of equations. Okay. Now you do not have to do this by hand. It's going to be messy to do by hand. So instead, we're going to do this in the calculator using a matrix. So I am going to hopefully remind you, because you should have done this last year. So hopefully this is a quick reminder of how to use your calculator to solve a matrix. All right, here we go. So I did a little snipping here so you could see some things, but I'm going to also open the calculator and go step by step through it with you. But this is at least here, this is the final answer when we're done here. So remember that the matrix information is under or above, I guess, the x to the negative 1. So second inverse x is what you're going to type. So let me get my computer to open my calculator here. So I'll talk through the steps. Again, pause if you need to, or come back to it and watch it again to remind yourself how to do these steps. Okay. So the first thing you're going to do is you're going to do second matrix so that you have this screen, and you're going to go over to edit. And you can choose any one of these you want, but notice I only have one of them that's already started. You could choose B, C, whatever, but you're going to have to create it. So I'm going to choose one, and it needs to be a 2 by 3 matrix. Okay, so if it's not, change the number. So if I write 3 by 3, this will make it 3 rows by 3 columns. So I want a 2 row by 3 column matrix. Okay, so hit enter on each of those, and then you're going to type in exactly what each value is. So if you didn't already know, 0.707 is the square root of 2 over 2. So we're typing in square root of 2 over 2 is the first spot. And then the second one is a negative square root of 3 over 2. Oh, that's not what I typed. And then 0 in the third spot. And then the next row is also square root of 2 over 2. And then a half, and then 500. Okay, so once you have all of this typed in, you're going to exit the matrix, excuse me, and then go back in. So second matrix again, but now you're going to do matrix math as opposed to editing. So we're going to do matrix math. What you want is the RREF, which is almost at the bottom. So I'm actually going to arrow up. So I want it's B. So I want RREF. It stands for reduced row echelon form. Doesn't matter if you remember it. I just like to tell you. Okay, so it shows up on your home screen. Now you go back to the matrix, and now you want to do matrix names. You want to take the name of the matrix you want to solve for. Okay, and you're going to get this in the what's again called the reduced row echelon form. Okay, so this should turn out to look like this with a 1001 in these spots. If this doesn't happen, then your matrix can't be solved. So that means either you type something in wrong or it's just not possible to solve. So these are the values that you get off the matrix. So that's what I have here. And these are then the answers. So this was your X row, right? Like this is what X equals because this is what your X's were, and then this is what Y is, so this is what your Y values are. So the X's, I believe, were the right cable. So, oopsie, right cable as point or 448.289 pounds of tension, and the left cable has 366.025 pounds. Okay. So let me go back just so you can see how this worked out. So here was the matrix that we put in the calculator. So when I said this was the X spot, so X's were in the first column and Y's were in the second column. And so when our matrix turned out to be 1, 0, 0, 1, with this being the X column, in this spot I have X is 1 and I have Y is 0. So I literally have 1X equals, and then it was the number that you have in this blank here. No X's here, 1Y equals, and it's the number you have in that spot. So that's how that table works out for your answer. Okay, so there's the two answers there. And then there's one more problem that you can try. I have given you the answers. They're almost identical to each other. I want you to give it a go. And if you get stuck on it, this is something, again, we can talk about together, maybe in a group chat. All right. Hope everyone's doing well, and we'll talk to you soon.